Have you ever wondered what it would feel like to fall into a place where the very laws of physics bend and break, where time itself stops making sense and space curves so violently that not even light can escape? A black hole is not just a region of darkness. It's a boundary beyond which reality transforms into something we can barely imagine. Tonight, we drift toward that edge, toward the event horizon, and ask not just what happens inside a black hole, but whether inside even has meaning anymore. So close your eyes, let the silence of deep space settle around you, and follow me into the most mysterious objects in the universe. Before we begin, if you're kind enough, a gentle like or a quiet tap on subscribe would mean the world to me. It's a small gesture, but I hold it with deep gratitude, because every bit of your support keeps this tiny universe alive and reminds me that these quiet stories still find their way to gentle hearts like yours. Now, let's begin with the first question. Part 1. What is a black hole? Really? The name itself sounds poetic. A black hole, a void, a tear in the fabric of existence. But the reality is far stranger than poetry. A black hole isn't a hole at all. It's an object so dense, so massive, that it warps space-time around itself into a trap from which nothing can return. According to NASA's Goddard Space Flight Center, a black hole is a region of space-time where gravity is so strong that nothing, not even particles traveling at the speed of light, can escape from it. It's not that light gets absorbed or destroyed, it's that the geometry of space itself prevents escape. Imagine space-time as a smooth rubber sheet. Place a marble on it, and it creates a small dip. Place a bowling ball, and the dip becomes deeper. Now, imagine an object so heavy, so concentrated, that it tears through the sheet entirely, creating an infinitely steep well. That's a black hole. Not a hole in space, but a place where space curves so sharply that all paths lead inward. Black holes form in several ways, but the most common occurs when a massive star at least 20 times the mass of our sun reaches the end of its life. For millions of years, the star burns hydrogen in its core, producing energy that pushes outward, balancing the crushing force of gravity pulling inward. But when the fuel runs out, that balance shatters. Without outward pressure, gravity wins. The star's core collapses in less than a second, compressing billions of tons of matter into a space smaller than a city. The result is a supernova, a brilliant explosion visible across galaxies, and at the center, where the core once was, a black hole is born. This process was first theorized by physicist Subrahmanyan Chandrasekhar in the 1930s. He calculated that any star above a certain mass, now called the Chandrasekhar limit, cannot resist its own gravity once fusion stops. The core collapses indefinitely, creating what physicists call a singularity, a point of infinite density where the known laws of physics break down. As ESA's XMM Newton mission describes, the singularity is not a place in space, but a point in space-time where curvature becomes infinite. But even before you reach the singularity, you encounter something equally mysterious: the event horizon. This is the boundary of no return, the invisible surface surrounding a black hole beyond which escape is impossible. The event horizon isn't a physical wall, it's a mathematical surface, a point of no return defined by the black hole's gravity. Once you cross it, every direction in space points toward the singularity. Forward, backward, left, right, up, down. All paths lead inward. According to Einstein's general relativity, the event horizon marks the place where the escape velocity equals the speed of light. Since nothing can travel faster than light, nothing can escape. The size of the event horizon depends on the black hole's mass. For a black hole with the mass of our sun, The event horizon would be about 3 kilometers in radius. For a supermassive black hole, like the one at the center of our Milky Way galaxy, the event horizon stretches millions of kilometers across. NASA's Event Horizon Telescope captured the first image of a black hole shadow in 2019, showing the dark silhouette of the event horizon surrounded by a glowing ring of superheated gas. That glowing ring isn't the black hole itself, it's the accretion disk, a swirling mass of gas, dust, and debris spiraling inward at nearly the speed of light. Friction within the disk heats the material to millions of degrees, causing it to emit X-rays and gamma rays. This radiation is what astronomers detect from Earth. The black hole itself emits nothing. It is, by definition, invisible. Yet black holes are not entirely silent. In 2015, the LIGO Observatory detected gravitational waves, ripples in space-time caused by 2 black holes merging 1.3 billion light-years away. As they spiraled toward each other, they released more energy in a fraction of a second than all the stars in the observable universe combined. The collision created a new, larger black hole and sent shock waves through the fabric of space itself. ESA's LISA mission, planned for the 2030s, will detect even fainter gravitational waves, allowing scientists to study black holes across cosmic history. Black holes come in different sizes. Stellar mass black holes, formed from collapsed stars, range from a few to a few dozen times the Sun's mass. Intermediate mass black holes, still mysterious, may exist in dense star clusters. And supermassive black holes, millions to billions of times the Sun's mass, lurk at the centers of most galaxies, including our own. The supermassive black hole at the heart of the Milky Way, called Sagittarius A, has a mass of about 4 million suns. Despite its immense mass, its event horizon is only about 12 million miles across, smaller than Mercury's orbit. Scientists believe supermassive black holes formed early in the universe's history, possibly from the direct collapse of massive gas clouds or from the mergers of countless smaller black holes. The James Webb Space Telescope has observed galaxies less than 500 million years after the Big Bang, and many already contain supermassive black holes. This suggests these giants formed quickly, growing by consuming gas, stars, and even other black holes over billions of years. But despite their power, black holes are not cosmic vacuum cleaners. They don't suck in everything around them. If the Sun were replaced by a black hole of equal mass, Earth's orbit wouldn't change. We'd continue circling at the same distance, though without sunlight, life would end quickly. A black hole's gravity only becomes inescapable near the event horizon. Far away, it behaves like any other massive object. What makes black holes truly strange is what happens to time near them. According to general relativity, the stronger the gravitational field, the slower time flows. Near a black hole's event horizon, time slows dramatically. An observer watching from a safe distance would see an object approaching the horizon move slower and slower, its light redshifting into invisibility. The object would appear frozen at the edge, never quite crossing. But from the perspective of the falling object, time feels normal. It crosses the horizon in finite time, unaware that to the outside universe, it appears suspended forever. This effect, called gravitational time dilation, has been confirmed by experiments on Earth. Atomic clocks placed at different altitudes tick at different rates, with clocks in stronger gravitational fields running slower. Near a black hole, the effect becomes extreme. A clock near the event horizon would tick thousands or millions of times slower than one far away. So when we ask what a black hole really is, the answer is both simple and profound. It's a region where gravity bends space-time so sharply that the usual rules of cause and effect, of past and future, of inside and outside, begin to dissolve. It's a place where the universe shows us the limits of what we can know, where physics itself reaches a boundary. As physicist Kip Thorne once said, "Black holes are the most perfect macroscopic objects in the universe, the only objects whose structure is determined entirely by the laws of physics." Take a slow breath. Even now, the nearest known black hole, Gaia BH1, lies about 1/600 light years away, silently warping the space around it. You are safe, floating in a gentle corner of the cosmos. But understanding what black holes are is only the beginning. The real mystery lies in what happens when you cross that invisible boundary, when you fall beyond the point of no return. That's where our next chapter begins. Part 2. What would you feel falling toward a black hole? If you were to fall toward a black hole, the first thing you'd notice is that nothing seems different. Space looks normal. Stars shine as they always have. The black hole itself remains invisible, a patch of perfect darkness against the cosmos. But as you drift closer, subtle changes begin. The stars ahead of you, in the direction of the black hole, appear to shift and brighten. Light from behind you begins to redshift, dimming and stretching toward infrared. The entire sky warps, bending around the black hole's gravity. This effect, called gravitational lensing, occurs because the black hole's mass curves the path of light passing near it. The European Space Agency's Euclid mission studies this lensing effect to map dark matter. But near a black hole, the distortion becomes extreme. Light from stars behind the black hole bends around it, creating a bright ring, the photon sphere where light orbits the black hole in unstable circular paths. Some photons escape, others spiral inward, never to return. As you fall closer, you begin to feel something strange. Your feet, closer to the black hole, experience stronger gravity than your head. This difference in gravitational pull is called tidal force, and near a black hole, it becomes brutal. If you're falling feet first into a stellar mass black hole, the tidal forces would stretch your body vertically while compressing it horizontally, a process astrophysicists grimly call spaghettification. Your body would be pulled into a thin strand of atoms, torn apart long before you reach the event horizon. But if the black hole is supermassive, the story changes. Supermassive black holes have event horizons so large that tidal forces near the horizon are relatively weak. You could, in theory, cross the event horizon of a supermassive black hole and survive, at least for a while. According to calculations by physicists at the Harvard-Smithsonian Center for Astrophysics, an astronaut falling into Sagittarius A, the supermassive black hole at the Milky Way's center, would cross the event horizon without immediate harm. The tidal forces would only become deadly much closer to the singularity. As you approach the event horizon, time begins to behave strangely. To you, time feels normal. Your watch ticks steadily. Your heart beats regularly. But to an observer far away, watching through a telescope, your descent appears to slow. You move slower and slower, your image redshifting and dimming. The light from your body takes longer and longer to escape the black hole's gravity, stretched and delayed. Eventually, you appear to freeze just above the event horizon, your image fading to invisibility. From the outside universe's perspective, you never quite cross. You remain suspended at the edge, frozen in time forever. But from your perspective, something entirely different happens. You cross the event horizon in finite time. Perhaps a few seconds, perhaps a few minutes, depending on the black hole's size. There's no physical barrier, no wall to mark the crossing. One moment you're outside, the next you're inside. And the moment you cross, everything changes. The event horizon is a one-way membrane in space-time. Outside it, escape is difficult but possible with enough speed. Inside it, escape becomes impossible. Every future trajectory, every possible path through space, leads inward toward the singularity. Inside the event horizon, space and time swap roles. In normal space-time, you can move freely through space but only forward in time. Inside the event horizon, the singularity lies in your future the same way tomorrow does. Just as you cannot avoid tomorrow, you cannot avoid the singularity. According to general relativity, falling into the singularity is as inevitable as aging. It's not a place you move toward in space. It's a moment in your future that you cannot avoid. What would you see? As you fall, the universe behind you contracts into a shrinking circle of light. The stars compress into a bright ring, blue shifted and accelerated. Light from the entire history of the universe pours toward you, compressed and intensified. In theory, you could see the universe age and fast forward, galaxies forming and dying, stars igniting and fading, all in the moments before you reach the singularity. But this is speculation. No one has ever crossed an event horizon and returned to tell the story. Inside, the black hole's rotation also matters. If the black hole spins, it drags space-time around with it, creating a region called the ergosphere just outside the event horizon. Inside the ergosphere, nothing can remain stationary. Space itself rotates, pulling everything along. If you fell into a rotating black hole, called a Kerr black hole, you would spiral inward, carried by the rotation of space-time itself. Some physicists speculate that the most extreme Kerr black holes might contain a ring-shaped singularity instead of a point, and passing through that ring could, in principle, lead to strange regions of space-time, perhaps even other universes. But these ideas remain mathematical curiosities, far beyond what we can observe. NASA's Chandra X-ray Observatory has measured the spin rates of several black holes by observing the X-rays emitted from their accretion disks. Some black holes spin at nearly the maximum rate allowed by physics, dragging space-time so violently that matter near them moves at a significant fraction of the speed of light. These observations confirm that rotation is a fundamental property of black holes, encoded in their structure. As you fall deeper, tidal forces intensify. Even in a supermassive black hole, the pull becomes unbearable closer to the center. Your body stretches, atoms pulled apart by the curvature of space-time. Eventually, you reach the singularity, the point where space-time curvature becomes infinite. Here, the known laws of physics break down. General relativity predicts infinite density and infinite curvature. But physicists believe this is a sign that relativity itself is incomplete. Quantum mechanics, the physics of the very small, must somehow take over. But we don't yet have a theory that combines quantum mechanics and gravity, a theory of quantum gravity. Some physicists, including Stephen Hawking and Roger Penrose, have suggested that singularities might not exist as true infinities. Instead, quantum effects might prevent the formation of a singularity, replacing it with a region of extremely high but finite density. Others propose that singularities are hidden behind event horizons, shielded from the outside universe by what Penrose called cosmic censorship. According to this idea, nature forbids naked singularities, singularities without event horizons, ensuring that the breakdown of physics remains hidden from view. But for now, the singularity remains a mystery, a place where our best theories fail. It's a reminder that black holes are not just objects to study but puzzles that challenge the foundations of physics itself. As physicist John Wheeler, who coined the term black hole in 1967, once said, Black holes teach us that space can be crumpled like a piece of paper into an infinitesimal dot, that time can be extinguished like a blown-out flame, and that the laws of physics we have regarded as eternal and immutable are anything but. Take a breath. You are safe here, outside the event horizon, far from the singularity. But even from this distance, we can glimpse the profound strangeness of what lies beyond. And as we continue our journey, a new question emerges. If falling into a black hole is a one-way trip, what happens to the information you carry? Does it disappear forever, or does the universe find a way to preserve it? That paradox is where our next chapter begins. Part 3. Does information disappear inside a black hole? Physics has a sacred rule. Information cannot be destroyed. In every process, from chemical reactions to cosmic collisions, the total information about a system is conserved. You can scramble it, transform it, spread it across space, but you cannot erase it. This principle, rooted in quantum mechanics, is called unitarity, and it's as fundamental as the conservation of energy. But black holes seem to violate this rule. When something falls into a black hole and crosses the event horizon, it disappears from the observable universe. Its information, everything that defined it, mass, spin, charge, position, velocity, seems to vanish. And that creates one of the deepest mysteries in modern physics, the black hole information paradox. The paradox began in 1974, when Stephen Hawking made a startling discovery. Using quantum field theory, he showed that black holes are not entirely black. Near the event horizon, quantum fluctuations create pairs of virtual particles, one with positive energy and one with negative energy. Normally, these pairs annihilate each other almost instantly, but near a black hole's event horizon, one particle can fall in while the other escapes. The escaping particle becomes real, carrying energy away from the black hole. Over time, this process, now called Hawking radiation, causes the black hole to lose mass and eventually evaporate. According to Hawking's calculations, a black hole emits thermal radiation, a featureless glow that depends only on the black hole's mass, not on what fell into it. A black hole formed from a collapsed star emits the same radiation as one formed from a cloud of gas, or even from compressed encyclopedias. The radiation carries no information about what went in. As the black hole evaporates, the information seems to disappear, violating the principle of unitarity. Hawking himself called this a breakdown of predictability, a fundamental loss of information. The implications were profound. If information could be destroyed, then the universe's past could not be reconstructed from its present state. The deterministic nature of physics would be shattered. Quantum mechanics, which relies on unitary evolution, would be incomplete. For decades, physicists debated whether Hawking was right or whether some subtle mechanism preserved the information. In 1997, physicist Leonard Susskind and others proposed a solution. The information is not lost. Instead, it's encoded on the event horizon itself in a phenomenon called the holographic principle. According to this idea, all the information about the three-dimensional interior of a black hole is stored on its two-dimensional surface, much like a hologram encodes a 3D image on a 2D film. As the black hole evaporates, the information is gradually released in the Hawking radiation, encoded in subtle correlations between the emitted particles. This idea drew on earlier work by physicists Gerard 't Hooft and Charles Thorne, who suggested that the maximum information a region of space can contain is proportional not to its volume, but to its surface area. The event horizon acts as the ultimate information storage device. with each square Planck length roughly 10 to the power of 35 meters containing 1 bit of information. For a solar mass black hole, the event horizon contains about 10 to the power of 66 bits of information, a number almost beyond comprehension. But how does the information escape? Hawking radiation is thermal, meaning it appears random and featureless. How can it carry detailed information about what fell in? The answer, according to modern research, lies in quantum entanglement, the strange correlation between particles that Einstein called spooky action at a distance. When a particle falls into a black hole, it becomes entangled with particles in the Hawking radiation. Over time, these entanglements build up, encoding the information in subtle patterns too complex for current technology to decode. In 2020, a group of physicists, including Jeff Pennington, Ahmed Almhiri, and Don Marolf, made a breakthrough. Using tools from quantum information theory, they calculated the entropy, or information content, of Hawking radiation over time. They found that initially, entropy increases as expected, but after the black hole evaporates past a certain point, the entropy begins to decrease. This turnaround, called the Page curve after physicist Don Page, suggests that information is indeed preserved and eventually released. The key to their calculation was the inclusion of quantum extremal surfaces, hypothetical surfaces in space-time, that track how information flows between the black hole's interior and the outside universe. These surfaces show that the interior and exterior are entangled in a way that allows information to leak out gradually. As ESA's Planck mission has shown through measurements of quantum fluctuations in the early universe, entanglement is a fundamental feature of reality, operating even in the most extreme environments. Yet, the paradox is not fully resolved. We still don't know exactly how information is encoded in Hawking radiation, or how it can be extracted. The radiation appears thermal to any observer with limited capabilities, but an observer with perfect knowledge of all quantum states, an idealized super observer, could in principle reconstruct the information. This distinction between what's theoretically possible and practically measurable lies at the heart of the paradox. Some physicists propose even more radical solutions. One idea, called black hole complementarity, suggests that information both falls into the black hole and escapes in Hawking radiation, depending on the observer's perspective. An observer falling into the black hole sees the information cross the event horizon and head toward the singularity. An observer outside sees the same information encoded in the Hawking radiation. Both perspectives are correct, but they cannot be compared directly because no signal can travel from inside the event horizon to outside. This idea, championed by Susskind, preserves unitarity, but requires accepting that reality depends on the observer in a profound way. Another proposal involves the firewall paradox, introduced in 2012 by physicists Ahmed Almhiri, Donald Marolf, Joseph Polchinski, and James Sully. They argued that preserving information might require the event horizon to be a violent, high-energy barrier, a firewall that destroys anything attempting to cross it. This contradicts general relativity, which predicts the event horizon should be a smooth, uneventful surface. The firewall paradox highlights the tension between quantum mechanics and general relativity, two pillars of modern physics that don't yet fit together seamlessly. Resolving these paradoxes may require a theory of quantum gravity, a framework that merges quantum mechanics and general relativity. String theory, loop, quantum gravity, and other approaches attempt this unification, but none have been experimentally confirmed. Black holes, as the most extreme laboratories of space-time, may hold the key to discovering which theory is correct. As physicist Juan Maldacena who formulated the AD-S-CFT correspondence, a powerful tool linking gravity and quantum mechanics, once said, "Black holes are the hydrogen atoms of quantum gravity, the simplest systems where quantum and gravitational effects are both important." NASA's upcoming Nancy Grace, Roman Space Telescope, and ESA's Euclid mission will observe thousands of black holes across cosmic history, measuring their properties with unprecedented precision. While these observations won't directly solve the information paradox, they'll provide data to test theoretical predictions about black hole behavior, Hawking radiation, and the structure of event horizons. Meanwhile, the paradox reminds us of a profound truth. Black holes are not just astrophysical objects. They're theoretical laboratories where the deepest questions of physics collide. They force us to confront the limits of our understanding, to question whether information is truly fundamental, and to imagine what lies beyond the event horizon, not just in space, but in the structure of reality itself. Take a slow breath. The information that defines you, every atom, every thought, every memory, is part of the universe's vast quantum state. If you fell into a black hole, would that information be lost forever? Or would it somehow leak back out, encoded in radiation so faint and subtle that only the universe itself could read it? The answer is still being written. One calculation, one observation, one insight at a time. And as we ponder this mystery, another question arises. If black holes can radiate and eventually evaporate, what happens at the very end? When the last bit of mass disappears, what's left behind? That's the quiet ending we'll explore next. Part 4. What happens when a black hole dies? Black holes are not eternal. They fade slowly, radiating away their mass through Hawking radiation, a quantum process so faint that for most black holes, it's utterly negligible. A stellar mass black hole, formed from a collapsed star, emits Hawking radiation at a temperature of only a billionth of a degree above absolute zero. It absorbs far more energy from the cosmic microwave background than it radiates. For such black holes, evaporation would take vastly longer than the current age of the universe, roughly 10 to the power of 67 years for a solar mass black hole. But given enough time, in the unimaginably distant future, even the largest black holes will evaporate completely, and when they do, the final moments might be spectacular. Stephen Hawking's 1974 calculation showed that smaller black holes radiate more intensely than larger ones. A black hole's temperature is inversely proportional to its mass, meaning as it evaporates and loses mass, it gets hotter and radiates faster. This creates a runaway process. As the black hole shrinks, its temperature rises and it evaporates faster, shrinking even more rapidly. In the final seconds, the black hole becomes incredibly hot, millions or even billions of degrees, emitting a burst of high-energy particles and radiation. For a primordial black hole, a hypothetical tiny black hole that might have formed in the early universe, the evaporation process could be much faster. A primordial black hole with a mass of about 1 billion tons would have formed 13.8 billion years ago and be evaporating right now. In its final moments, it would release as much energy as millions of nuclear bombs, a flash of gamma rays, and particles visible across vast distances. NASA's Fermi Gamma Ray Space Telescope has searched for these evaporation bursts, but has not yet detected any, suggesting primordial black holes, if they exist, are rare. But what happens at the very end? When a black hole evaporates completely, does it leave anything behind? This question touches the deepest mysteries of quantum gravity. According to classical general relativity, the black hole simply disappears, leaving empty space. But quantum mechanics suggests something more subtle might occur. One possibility is that the black hole leaves behind a remnant, a tiny, stable object containing the black hole's residual information. These remnants would be incredibly dense, with masses comparable to the Planck, mass about 22 micrograms, but sizes comparable to the Planck length, about 10 to the power of 35 meters. They would be the smallest, densest objects possible, existing at the boundary between quantum mechanics and gravity. Some physicists propose these remnants could be scattered throughout the universe, invisible relics of ancient black holes that evaporated long ago. Another idea, proposed by physicist Carlo Rovelli and others working in loop quantum gravity, suggests that the singularity at a black hole's center might be replaced by a bounce, a quantum transition that connects the black hole's interior to a new region of space-time, possibly even a new universe. In this scenario, the black hole doesn't truly evaporate. Instead, it transforms, its interior expanding into a separate space-time disconnected from our own. This idea, called a black hole to white hole transition, remains speculative, but offers a tantalizing possibility that black holes are not endpoints but gateways. Hawking himself revised his views over the years. In 2004, he famously conceded a bet with physicist John Preskill, acknowledging that information might not be lost after all. He proposed that the event horizon is not as sharp a boundary as once thought, that quantum fluctuations might blur it, allowing information to leak out gradually. In his later work, Hawking explored the idea of soft hair, quantum imprints on the event horizon that encode information about what fell in. These soft hair modes, subtle quantum states associated with the black hole's gravitational field, could carry information in ways that thermal Hawking radiation does not. Recent theoretical work supports this idea. Physicists Andrew Strominger, Stephen Hawking, and Malcolm Perry showed that black holes possess an infinite number of conserved quantum charges associated with their soft hair. These charges encode information and are not erased during evaporation. As the black hole radiates, these charges are transferred to the emitted particles, preserving the information. This discovery suggests that black holes are far more complex than simple objects defined only by mass, spin, and charge. But observing black hole evaporation remains impossible with current technology. Even the smallest astrophysical black holes will exist for eons. The only way to study Hawking radiation is through indirect means, such as analog systems. Physicists have created laboratory analogs of black holes using sound waves and fluids, ultra-cold atoms, and even light and optical fibers. These systems mimic the event horizon's behavior, and in 2016, physicist Jeff Steinhauer reported observing the analog of Hawking radiation in a sonic black hole made from a Bose-Einstein condensate. While not a true black hole, the experiment confirmed key predictions of Hawking's theory. As black holes evaporate, they also release gravitational waves, faint ripples in space-time. ESA's planned LISA mission will detect gravitational waves from black hole mergers and other extreme events. In the far future, LISA's successors might detect the gravitational signature of evaporating black holes, providing direct evidence of Hawking radiation. What happens to the universe when all black holes have evaporated? In the distant future, after stars have died and galaxies have faded, black holes will be among the last surviving objects. They will absorb stray particles and radiation, growing slightly, but inevitably evaporating. When the last black hole disappears, the universe will enter a state of maximum entropy, a featureless expanse of nearly uniform radiation. Physicists call this the heat death of the universe, a state where no energy gradients exist, no structures form, and time loses meaning. It's the ultimate equilibrium, the final rest after countless eons of motion and change. But even in heat death, quantum fluctuations persist. According to quantum mechanics, empty space is never truly empty. Virtual particles pop in and out of existence, and over incomprehensible timescales, these fluctuations could spontaneously create new structures, even new universes. Some cosmologists speculate that our universe itself might be a quantum fluctuation, a rare event in an eternal multiverse. If so, then black hole evaporation is not an ending but a transition, one phase in an eternal cycle of creation and dissolution. Physicist Roger Penrose has proposed a related idea called conformal cyclic cosmology, which suggests the universe undergoes infinite cycles. In each cycle, the universe expands, cools, and eventually reaches a state dominated by radiation. At that point, the geometry of space-time loses its sense of scale, and the universe forgets its size, transitioning smoothly into the next Big Bang. In this framework, black hole evaporation plays a crucial role, erasing information and resetting the cosmic clock. Whether any of these ideas are correct remains unknown. Black hole evaporation operates on timescales so vast they dwarf the current age of the universe. We live in an epoch where black holes are growing, not evaporating, where stars still shine and galaxies still collide. But the mathematics predicts that eventually all black holes will fade and the universe will enter a new, quieter phase. Take a moment to reflect. The black hole nearest to Earth, Gaia BH1, will exist for trillions upon trillions of years, far longer than any human civilization, far longer than the stars themselves. Its slow evaporation is a reminder that even the universe's most permanent-seeming objects are temporary. The time erodes all things, even gravity's ultimate grip. And as we consider these endings, a new question emerges. If black holes can evaporate and disappear, might they also be created in ways we haven't yet imagined? Could tiny black holes exist in the quantum world, or even be created in laboratories? That strange possibility is where our next chapter leads. Part 5. Could we ever create a black hole? The idea sounds like science fiction, creating a black hole in a laboratory. But physics doesn't forbid it. If you compress enough mass into a small enough space, a black hole will form, regardless of what that mass is. The challenge is achieving the necessary density. For a black hole to form, matter must be compressed within its Schwarzschild radius, the radius at which the escape velocity equals the speed of light. For an object with the mass of Earth, that radius is about 9 millimeters. For a human, it's about 10 to the power of 25 meters, far smaller than an atomic nucleus. Creating such densities is far beyond current technology, but nature might do it for us. When the Large Hadron Collider at CERN smashes protons together at nearly the speed of light, it recreates the conditions of the early universe, generating temperatures and energies not seen since moments after the Big Bang. Some physicists speculated that if extra dimensions of space exist, as predicted by string theory, these collisions might create microscopic black holes. In theories with extra dimensions, gravity becomes much stronger at small scales, making it easier to form black holes. These micro black holes would be incredibly tiny, with masses far smaller than a single proton, and they would evaporate almost instantly through Hawking radiation. According to calculations by physicists Savas Dimopoulos and Greg Landsberg, such black holes would decay in about 10 to the power of 27 seconds, leaving behind a spray of particles detectable by the LHC's instruments. Despite extensive searches, no evidence of micro black hole production has been found. This doesn't rule out extra dimensions, but it sets strict limits on their size and properties. If extra dimensions exist, they must be smaller or configured differently than many theories predicted. The absence of micro black holes at the LHC also reassures the public. Even if they could be created, they would pose no danger. Hawking radiation ensures they evaporate faster than they could interact with surrounding matter. Beyond colliders, black holes might form naturally in extreme astrophysical environments. When two neutron stars collide, they release tremendous energy and create conditions of extreme density. Simulations by NASA's Goddard Space Flight Center show that some neutron star mergers might briefly form a hypermassive neutron star, an object teetering on the edge of collapse. If the merged object exceeds the maximum mass a neutron star can support, it collapses into a black hole within seconds or minutes. These events are now observed through gravitational waves, first detected by LIGO in 2017. In the early universe, conditions were even more extreme. In the first fractions of a second after the Big Bang, densities and temperatures were so high that tiny fluctuations in the distribution of matter might have collapsed directly into primordial black holes. These black holes would have a wide range of masses, from less than a gram to thousands of solar masses. Some physicists, including Stephen Hawking and Bernard Carr, proposed that primordial black holes might make up some or all of the universe's dark matter, the invisible substance that outweighs ordinary matter 5-to-1. NASA's Fermi Gamma Ray Space Telescope and ESA's Integral Observatory have searched for the gamma ray bursts that would result from evaporating primordial black holes. So far, no definitive detections have been made, but the search continues. If primordial black holes exist, they would be relics of the universe's earliest moments, fossils preserved since the Big Bang. Another speculative idea involves vacuum decay. According to quantum field theory, the vacuum of space might not be in its lowest energy state. If a lower energy state exists, the vacuum could spontaneously transition to it, releasing enormous energy. Some physicists have speculated that this transition might create a bubble that collapses into a black hole. However, these ideas remain highly theoretical, with no experimental evidence to support them. Could advanced civilizations create black holes intentionally? Some futurists and physicists have speculated about using black holes as energy sources. A rotating black hole, a Kerr black hole, stores rotational energy that can, in principle, be extracted through a process called the Penrose process. By dropping matter into the ergosphere, the region just outside the event horizon where space-time is dragged along with the black hole's rotation, energy can be extracted and sent outward. Physicist Roger Penrose proposed this mechanism in 1969, and later work showed it could be highly efficient, converting up to 29% of the black hole's mass into usable energy. An even more advanced concept, proposed by physicist John Archibald Wheeler, and later elaborated by science fiction writers, is the Kugelblitz, a black hole formed not from matter, but from concentrated light. If enough photons are focused into a small enough region, their combined energy would create a gravitational field strong enough to form a black hole. Calculations suggest that a Kugelblitz, with the mass of a small asteroid, would radiate Hawking radiation at temperatures useful for energy production. Such a black hole could serve as a compact power source for advanced spacecraft or even civilizations. However, creating a Kugelblitz requires technology far beyond anything currently imaginable, including the ability to focus and contain energy densities millions of times greater than those in nuclear explosions. Despite these speculative ideas, no black hole has ever been created artificially, and none will be in the foreseeable future. The energies required are simply too vast. Even the most powerful particle colliders, nuclear reactors, and lasers fall short by many orders of magnitude. Nature remains the only black hole factory we know, but the question of whether we could create a black hole touches something deeper: the relationship between knowledge and power. As we uncover the laws governing black holes, we approach a threshold where understanding becomes capability. Just as discovering nuclear fission led to both energy production and weapons, understanding black holes might one day lead to technologies we can barely imagine. Harnessing the energy of black holes, traversing space-time through wormholes, or even engineering space-time itself might be possible for sufficiently advanced civilizations. Physicist Freeman Dyson once speculated about the far future of intelligence in the universe. He imagined civilizations outlasting the stars, adapting to an ever-cooling cosmos, perhaps even using black holes as the last sources of energy and computation. In Dyson's vision, black hole evaporation provides a faint but finite energy source that could sustain thought for eons, allowing consciousness to persist even in the universe's twilight. For now, black holes remain beyond our control, objects to observe and study, not to create or manipulate. But the fact that physics allows their creation, at least in principle, reminds us that the universe's laws are universal. The same principles that govern stellar collapse also apply in particle colliders. Early universe cosmology, and perhaps one day advanced technology. Take a breath. The black holes we observe, scattered across the galaxy and beyond, formed naturally, sculpted by gravity and time. But the possibility that black holes could be created, whether by nature in the early universe or by advanced civilizations in the far future, hints at the profound depth of physics, at the way understanding and possibility are intertwined. And as we contemplate this possibility, another question emerges. If black holes can be created, might they also be destroyed, not through slow evaporation, but through some more dramatic process? Could a black hole be disrupted, torn apart, or transformed? That strange frontier is where our journey leads next. Part 6. Can anything destroy a black hole? Black holes seem indestructible. They devour stars, absorb light, and trap anything that crosses their event horizon. But are they truly invincible? Can anything disrupt or destroy a black hole? The answer is subtle. Black holes can be destroyed, but only through processes that take unimaginable amounts of time or require conditions we've never observed. The first and most certain way a black hole can be destroyed is through Hawking radiation. As we've discussed, black holes emit faint thermal radiation, slowly losing mass. Over timescales of 10 to the power of 67 years or more, even supermassive black holes will evaporate completely. This is not destruction in the usual sense, not a violent event, but a gradual fading, a slow return of mass and energy to the universe. It's the only confirmed mechanism for black hole destruction, though we've never observed it directly. But what about more dramatic scenarios? Could a black hole be torn apart or neutralized? In principle, if you could reduce a black hole's mass below a certain threshold, it would cease to exist as a black hole. But removing mass from a black hole is nearly impossible. Any matter or energy you throw at it only makes it larger. Even light, despite having no mass, carries energy and momentum, which adds to the black hole's mass energy. One speculative idea involves colliding two black holes in just the right way. When black holes merge, they form a larger black hole and release energy as gravitational waves, But what if the collision could somehow disrupt the event horizon? In practice, this doesn't happen. The mathematics of general relativity shows that event horizons are remarkably stable. Once formed, they can merge and grow, but never split or shrink except through Hawking radiation. This is encapsulated in the second law of black hole mechanics, proposed by physicist Jacob Bekenstein, which states that the total area of all event horizons in the universe can never decrease, at least in classical physics. However, quantum mechanics introduces subtleties. If Hawking radiation is real, and most physicists believe it is, then the event horizon area can decrease over time. But this is a slow, steady process, not a sudden rupture. Even the most energetic imaginable collision or explosion cannot break an event horizon. What about exotic matter? Physicists speculate about matter with negative energy density, which could, in principle, exert repulsive gravity. If enough negative energy matter could be concentrated near a black hole, it might counteract the black hole's gravity, preventing collapse and potentially destabilizing the event horizon. Such matter appears in solutions to Einstein's equations, such as wormholes, which require negative energy to stay open. However, no naturally occurring negative energy matter has ever been observed, and quantum field theory places strict limits on how much negative energy can exist and where. Another radical idea involves the cosmic censorship hypothesis, proposed by Roger Penrose. The hypothesis states that singularities, regions where space-time curvature becomes infinite, are always hidden behind event horizons. If a process could create a naked singularity, a singularity visible from the outside universe, it would represent a breakdown of predictability, a place where the laws of physics fail openly. Some physicists have explored whether extreme conditions, such as rapidly spinning a black hole beyond its theoretical limit, could destroy the event horizon and expose the singularity. But calculations suggest nature prevents this, that any attempt to overspin a black hole is thwarted by physical limits on energy and angular momentum. There's also the question of whether black holes can be destroyed by information theoretic means. If the black hole information paradox is resolved by the idea that information is encoded on the event horizon and released through Hawking radiation, then in a sense, the black hole's destruction is also the information's release. The black hole gradually dissolves, its encoded information leaking back into the universe, ensuring nothing is truly lost. In the realm of speculative physics, some theories propose that black holes might not be permanent. Loop, quantum gravity, an approach to quantum gravity, suggests that the singularity at a black hole's center is replaced by a region of extremely high, but finite, curvature. In this framework, the interior of a black hole might undergo a quantum transition, a bounce that connects it to another region of space-time, perhaps even a new universe. If this is true, black holes are not destroyed but transformed, their interiors becoming the seeds of new spacetimes. Another idea, proposed by physicist John Wheeler and later explored in various forms, is the concept of a black hole bomb. If you place a reflective shell around a rotating black hole and send in waves of a certain frequency, the waves can bounce back and forth between the shell and the black hole, extracting energy from the black hole's rotation through the Penrose process. In principle, this could slow the black hole's spin and extract its rotational energy, though it wouldn't destroy the black hole itself, only change its properties. In the far future, when the universe has expanded to the point where galaxies are separated by vast empty voids, black holes might be the last significant structures. As they evaporate, they'll release their mass energy back into space, contributing to the universe's eventual heat death. In that sense, black holes are temporary structures, destined to fade like everything else. Their destruction is slow and inevitable, written into the laws of thermodynamics and quantum mechanics. But in the here and now, black holes are as close to indestructible as anything in the universe. They can grow by absorbing matter and energy. They can merge, forming larger black holes. They can slowly evaporate through Hawking radiation, but they cannot be smashed, blown up, or disassembled by any known force or technology. They are the universe's ultimate strongholds, regions where gravity reigns supreme and escape is impossible. This invincibility, however, is not absolute. It's a consequence of the laws of physics as we currently understand them. If new physics is discovered, if quantum gravity reveals unexpected phenomena, our view of black holes might change. Perhaps future theories will show that event horizons are not as absolute as they seem, that information is not merely encoded but can be extracted, that black holes are not endpoints but transitions. Take a slow breath. The black holes we observe today, from stellar mass remnants to supermassive giants, will outlast the stars, the galaxies, even the cosmic structure we call home. But they are not eternal. Given time, enough time, they will fade, their energy dispersed, their information released, their grip on space-time finally relaxed. And as we consider the ultimate fate of black holes, a deeper question arises. If black holes can eventually be destroyed, does that mean the universe itself is temporary? If everything, even the most extreme objects, fades away, what does that say about the nature of existence? That question leads us to our next chapter, where we explore not just black holes, but the universe's ultimate destiny. Part 7. What do black holes tell us about the universe's fate? Black holes are more than cosmic curiosities. They are clues, signposts pointing toward the universe's ultimate fate. By studying how they form, evolve, and evaporate, we glimpse the long arc of cosmic history, from the first stars to the final fading of the last light. Black holes, in their quiet persistence, reveal truths about energy, entropy, and the eventual destiny of everything. The universe began in a state of extremely low entropy, a highly ordered configuration with energy concentrated in a small, hot region. Since the Big Bang, entropy has increased, energy has spread out, and structure has become more diffuse. This is the second law of thermodynamics. In any closed system, entropy never decreases. The universe, as far as we know, is the ultimate closed system, and its entropy has been rising for 13.8 billion years. Black holes play a crucial role in this story. According to Jacob Bekenstein's work in the 1970s, black holes possess entropy proportional to the area of their event horizons, not their volume. This was a profound discovery, suggesting that black holes are thermodynamic objects, capable of storing vast amounts of entropy. A solar mass black hole has an entropy of about 10 to the power of 54, measured in fundamental units. A supermassive black hole, with billions of solar masses, has an entropy trillions of times higher. In fact, black holes are the most entropic objects in the universe. Nothing else can store as much disorder in as compact a form. When a star collapses into a black hole, the entropy of the system increases dramatically. The star's complex structure, its layers, its fusion reactions, all that information is compressed and hidden behind the event horizon. From the outside, the black hole appears simple, defined only by mass, spin, and charge. But the entropy encoded on the event horizon accounts for all the lost complexity. This realization led Stephen Hawking to propose that black holes emit thermal radiation, confirming that they are not just gravitational objects, but thermodynamic ones. As the universe ages, black holes will dominate. Stars will die, galaxies will merge, and eventually, most matter will either fall into black holes or be expelled into intergalactic space. After roughly 1 trillion years, star formation will cease. The universe will darken, lit only by the faint glow of cooling white dwarfs, dim red dwarfs, and the occasional flash of matter falling into black holes. During this era, called the black hole epoch, black holes will be the universe's primary structures, but black holes too are temporary. Through Hawking radiation, they evaporate, returning their mass energy to space. A solar mass black hole will take about 10 to the power of 67 years to evaporate. A supermassive black hole, with 1 billion solar masses, will last about 10 to the power of 100 years. These timescales are so vast they defy comprehension. For comparison, the current age of the universe is only 1.38 times 10 to the power of 10 years. The black hole epoch will last 1 trillion times longer than the universe has existed so far. After all black holes evaporate, the universe will enter its final phase, heat death. Energy will be spread uniformly, with no gradients to drive motion, no stars to shine, no structures to form. Only a faint, cold sea of photons and neutrinos will remain, drifting through an ever-expanding void. The temperature will approach absolute zero, and time, in any meaningful sense, will lose its significance. Nothing will happen because there will be no energy available to make anything happen. This scenario, based on the second law of thermodynamics and general relativity, paints a bleak picture, but it's not the only possibility. Some cosmologists speculate about cyclic models, where the universe undergoes infinite cycles of expansion and contraction. Physicist Roger Penrose proposed conformal cyclic cosmology, where the heat death of one universe becomes the Big Bang of the next. In his model, the universe's geometry loses track of scale at the end of each cycle, allowing a smooth transition into a new beginning. Black hole evaporation plays a key role, erasing structure and resetting entropy. Other theories involve the multiverse, the idea that our universe is one of many, each with its own laws and constants. In this framework, black holes might be more than endpoints. Some physicists, including Lee Smolin, have speculated that black holes could give birth to new universes. When a black hole forms, its interior might undergo a quantum transition, expanding into a new space-time disconnected from ours. If true, our universe itself might be the interior of a black hole in a larger parent universe. This idea, called cosmological natural selection, suggests the multiverse evolves, with universes that produce many black holes giving rise to more offspring universes. These ideas remain speculative, but they highlight how black holes challenge our understanding of endings and beginnings. They are not just destroyers, but potential creators, not just endpoints, but transitions. ESA's Euclid mission and NASA's upcoming Nancy Grace Roman Space Telescope will study the universe's expansion and the distribution of dark energy, the mysterious force accelerating cosmic expansion. Their observations will help refine our understanding of the universe's long-term fate, including the role black holes play in it. Black holes also teach us about the deep connection between gravity, thermodynamics, and information. The holographic principle, which grew out of black hole thermodynamics, suggests that all the information in a three-dimensional region of space can be encoded on its two-dimensional boundary. This idea, developed by Gerard 't Hooft, Leonard Susskind, and others, implies that the universe itself might be a hologram, with its fundamental reality existing on a distant boundary. If true, This would radically change our understanding of space, time, and existence. Moreover, black holes remind us that the universe is not static. It has a history, a trajectory, a story that unfolds over incomprehensible timescales. The black holes we see today are young, formed recently in cosmic terms. But in the deep future, when the last stars have died and the universe is dark and cold, black holes will be ancient relics, slowly evaporating, releasing the last whispers of energy into the void. What will remain when the last black hole evaporates? According to current physics, only a faint background of radiation, photons, and neutrinos, stretched and redshifted by the universe's expansion. The cosmos will be empty, silent, and still. But even in that emptiness, quantum fluctuations will persist. Tiny ripples in space-time that might, over incomprehensible timescales, create new structures, perhaps even new universes. The vacuum is never truly empty, and the laws of quantum mechanics ensure that even in heat death, the potential for change remains. Physicist Freeman Dyson once explored whether life could persist in such a universe. He concluded that if intelligence could adapt, slowing its metabolism to match the decreasing energy availability, it might survive indefinitely, thinking slower and slower thoughts in an ever-expanding cosmos. Black holes, in this scenario, would serve as the last energy sources, their evaporation providing faint power for computation. It's a strange, melancholy vision, but one that honors the resilience of complexity and the persistence of information. Take a quiet breath. The black holes that exist today, from the stellar remnants scattered through the galaxy to the supermassive giants at the centers of galaxies, are part of a story larger than themselves. They are chapters in the universe's long arc, from order to disorder, from the Big Bang's intense heat to the cold silence of heat death. And in their slow evaporation, they remind us that even the universe's most enduring structures are temporary, that nothing lasts forever, not stars, not galaxies, not even black holes. And yet, within that impermanence lies a strange beauty. The universe's story, however it ends, is one of transformation. Energy changes form, information flows, structures arise and dissolve. Black holes are not just endpoints, but transitions, moments where the universe reveals its deepest principles. As we study them, we study not just gravity or quantum mechanics, but the nature of time, entropy, and existence itself. Now, as we approach the end of our journey, one final question remains. If black holes reveal so much about the universe, what do they reveal about us? What does it mean that we, tiny beings on a small planet, can peer into the heart of these cosmic monsters and understand, even if only partially, what happens inside? That reflection is where our story gently concludes. Part 8. What do black holes teach us about ourselves? We are made of stardust, atoms forged in the hearts of dying stars and scattered across space in supernova explosions. Every element in your body, except hydrogen, was created in stellar furnaces or in the violent collisions of neutron stars. In a very real sense, you are the universe observing itself, a temporary arrangement of matter and energy capable of thought, wonder, and curiosity. Black holes, the most extreme objects in the cosmos, remind us of this connection. They are not separate from us. They are part of the same physical reality, governed by the same laws that shape atoms, planets, and minds. The fact that we can understand black holes, at least partially, is itself profound. It means the universe is comprehensible, that the patterns governing the fall of an apple also govern the collapse of a star, that the mathematics of space-time can be grasped by minds evolved to navigate forests and plains. This comprehensibility is not guaranteed. The universe could have been chaotic, its laws changing from place to place or moment to moment, but it's not. The laws of physics are universal, the same on Earth as in the most distant galaxy, the same today as billions of years ago. This consistency allows us to predict, to test, to understand. And black holes, despite their strangeness, obey these laws. They are solutions to Einstein's equations, quantum objects subject to Hawking radiation, thermodynamic systems governed by entropy. The journey to understand black holes has been a human journey, shaped by curiosity, creativity, and collaboration. It began with Isaac Newton's laws of motion and gravity, which described how objects fall. It continued with Albert Einstein's general relativity, which revealed that gravity is the curvature of space-time. It advanced with quantum mechanics, which showed that even the vacuum of space is alive with fluctuations. And it continues today, with thousands of scientists worldwide using telescopes, detectors, and supercomputers to probe the universe's mysteries. Each discovery about black holes is also a discovery about the limits of human knowledge and the power of human imagination. When Carl Schwarzschild solved Einstein's equations in 1916, just months after general relativity was published, he found a solution describing what we now call a black hole. Einstein himself doubted such objects could exist, thinking nature would prevent their formation. But astronomers proved otherwise. In the 1960s, observations of quasars and X-ray sources suggested massive, compact objects devouring matter. By the 1990s, the evidence was overwhelming. Black holes were real. The first image of a black hole's shadow, captured by the Event Horizon Telescope in 2019, was a triumph of human ingenuity. It required coordinating radio telescopes across the globe, from Hawaii to Chile to Antarctica, creating an Earth-sized virtual telescope. The image showed the shadow of the supermassive black hole at the center of galaxy M87, surrounded by a ring of glowing gas. It was not just a picture. It was confirmation that black holes exist exactly as Einstein's equations predicted, a century after those equations were written. Black holes also teach us humility. They remind us that the universe is vast, ancient, and indifferent. A black hole does not care about life, consciousness, or civilization. It simply exists, a consequence of gravity and mass. Yet, within that indifference lies a strange kind of beauty. The universe's laws are elegant, symmetric, profound. The same equations that describe black holes also describe the orbits of planets, the bending of light, the flow of time. There is a unity to physics, a deep interconnectedness that black holes help reveal. Moreover, black holes challenge us to confront the unknown. We don't fully understand what happens at the singularity. We don't know how to reconcile quantum mechanics and general relativity. We don't know if information is truly preserved or if the holographic principle is correct. These gaps in our knowledge are not failures but opportunities. They are frontiers waiting to be explored, questions that might lead to new physics, new theories, new ways of understanding reality. In studying black holes, we also confront our own limitations. We cannot visit a black hole, cannot peer inside an event horizon, cannot test our theories directly in the most extreme conditions. We must rely on indirect evidence, on gravitational waves, on X-rays from accretion disks, on simulations and calculations. This requires trust in mathematics, in logic, in the scientific method. It requires accepting that some knowledge is forever out of reach, that some questions may never have answers. Yet the progress we've made is remarkable. A century ago, black holes were purely theoretical, mathematical curiosities. Today, we detect them regularly, measure their masses and spins, observe them merging, and study their effects on surrounding matter. The LIGO and Virgo observatories have detected dozens of black hole mergers through gravitational waves. The Event Horizon Telescope has imaged 2 black holes. The James Webb Space Telescope is revealing black holes in the early universe, formed when the cosmos was young. Each observation adds to our understanding, refining our theories and raising new questions. Black holes also inspire. They appear in art, literature, film, and philosophy. They capture the imagination because they represent the ultimate mystery, the boundary between the known and the unknowable. They symbolize transformation, the idea that endings can be beginnings, that destruction and creation are intertwined. They remind us that the universe is stranger and more wondrous than we often realize. In a practical sense, studying black holes has driven technological innovation. The techniques developed to detect gravitational waves required the most sensitive instruments ever built, capable of measuring distortions in space smaller than a proton. These technologies have applications beyond astronomy, in precision measurement, materials science, and quantum computing. The algorithms used to create black hole images advance data processing and machine learning. Science, even when it seems purely abstract, often leads to unexpected benefits. But perhaps the deepest lesson black holes teach us is about perspective. From the vantage point of a black hole, the universe looks different. Time and space swap roles. Light bends into impossible paths. The future becomes inevitable, encoded in the curvature of space-time. Yet from our perspective here on Earth, life goes on. We look up at the night sky, see stars and galaxies, and marvel at the fact that we can understand any of it. We are brief, fragile beings, alive for a moment in cosmic time. But in that moment, we can reach across space and time, probe the hearts of dying stars, detect ripples in space-time, and ask questions that touch the deepest mysteries. Black holes, for all their strangeness, are part of our story. They are made of the same matter, shaped by the same forces, described by the same mathematics. In understanding them, we understand ourselves, our place in the cosmos, and the nature of reality itself. Take a final, slow breath. The black holes scattered across the universe, silent and invisible, continue their slow dance through space-time. They grow, they merge, they evaporate. They warp the fabric of the cosmos and challenge the boundaries of human knowledge. And in doing so, they remind us that we are part of something vast, something ancient, something profoundly beautiful. The universe is not just a place we inhabit, it is what we are. And black holes, the strangest objects in that universe, are mirrors reflecting back to us the limits of knowledge, the power of curiosity, and the enduring mystery of existence itself. If this quiet journey has brought you even a small moment of peace, I'm deeply grateful you've spent it here with me. A gentle like or a soft tap on subscribe means more than you can imagine. It's what keeps me creating these cosmic lullabies for wandering minds like yours. And if you're kind enough, please tell me in the comments where you are tonight and what time it is where you're listening. I love seeing how far these quiet adventures drift across the world, from one sleepy corner of the planet to another. Your words, your presence, even your silence, they're like little stars guiding me forward, and I treasure them deeply. Until next time, may the universe turn softly around you, and may the mysteries of the cosmos bring you wonder and rest.